All right, now that Anil is here, we can really start. So if you remember, last week we implemented a dense, contiguous, homogeneous container, also known as an array. Yes. And okay, so just to give you a sense for where all of this is going, right? Ultimately, we want to implement a variable length container that can hold things of variable lengths. And to do that, we need to, we just don't want to dump the entire code on the class. We want to explain why we are doing what we are doing, why things are designed the way they're designed. So basically, we need to look at the design of a few simple containers to set that up. Well, Michael forgot something. So that's why we're looking at a few simple containers first. And today, hopefully in this class, we'll be developing one of the first pieces of code that will actually go into the final library that we intend to develop, right? So let's look at array once again. This is the same code we wrote last week. I've just moved it to a .h file. So remember, let me just point out a few things we noted about this. We have only one member variable here, right, called data. And note that even though array had a fairly wide interface, we actually used this private, well, it's not private, but this member variable in like 3 places or 4 places. Swap and begin, basically those 2 functions, and the rest of the interface was all implemented in terms of just those functions. Right? Same thing with the only other thing in this class is the size k, and that again occurs in basically that one location. Right? So this is an important thing to note, because often with many data structures we will find that even though you have a large rich interface, the code is actually very small. So the fact that the 2 things that we would think of as private members are only used in 3 functions basically tells you that you can implement everything else in terms of that. Right? Everything else is implementable in terms of that very basic interface. So this is going to come up again today. This is something important to keep track of. Another thing about the array is we didn't really need to implement any iterators, because a pointer is a perfectly good iterator for an array, right? For the variable length types that we are going to work on, iterators are going to be very important. And so we do really need to understand iterators very well. And so today we're going to spend most of our time writing iterator adapters, interesting kinds of iterators to do various things with the array. And hopefully that will give us a strong understanding of what an iterator is. So you've all probably heard of iterators, right? You've probably heard that an iterator is a generalization of a pointer, yes, and all of the types that, all of the operations that you can do on an iterator are basically operations you can do on a pointer. Right? For those of you coming from other languages, the term iterator is not ideal. Like it took me a long time before I could think of iterator without having to mentally translate it into something like coordinate. If you think of it as coordinate or position, it makes a lot more sense. And if you have trouble thinking about iterators, try that. I highly recommend that. So, without further ado,
so what is an iterator adapter?
We will find out. Okay, so remember, we had this example code we wrote, right? Here we define an array of size 10, and we had this nice little function called print range, which took a begin, iterator, and last, printed the whole thing. We could print our array very easily, right? No problem. Then we defined an array of pairs. So this is an array of pairs of ints containing 3 pairs. And then we said, okay, we want to print out just the second element of the pair. And we have a function called print range, but that doesn't quite work here because it will print the entire object. Right? What we want is an iterator. We want to be able to hand print range something that iterates over just, let's say, the second value, or maybe the first value. If you've used if you've used Python, you've probably used iter keys and iter values functions, which are very useful. I mean, you use them all the time, right? So we want something like that, and we don't want to have to write a separate loop to do that, because I mean, this is print. What about sort? What about find if? There are lots of functions that are defined in terms of a range. You might want them to work slightly differently. Maybe you want them to not work on the entire pair, but a part of the pair. So let's try to make something like that. Okay. So before I start writing code, let us just clarify what we mean exactly. Go down to the bits. Think about what do we want to do here, and then we can start implementing that. Right? So we have an array of pairs. A pair is basically two things. So what is an iterator over that array? Let's say I have some value here. This is a pointer. It goes here, right? So if I just take a normal iterator pointer into that, what operations can I do on it? We just went over the list, right? You can dereference it, and you can increment it. Anything else? You can, yeah. So in this case, this is a random access iterator, so you can decrement it, and you can actually increment it by any number of things, and you can take differences. But let's focus on forward. So for forward access, it's really just dereference and increment, right? So let's think about this. Was there a question? And compare, yes, very important. I mean, without compare, things would not work. So the default iterator we have, when we dereference, what do we get? We get a reference to this object that it is pointing to, yes? And when we increment, what happens? When we increment, we change the value such that it starts pointing at the next guy, right? What we want to do is, we want to be able to call print range. And we want to give it something that will, so let's call that thing iter second, okay? Of begin of x2, iter second, end. And what we want, what behavior do we want here? What behavior we want is that when we dereference, what do we get? We get this instead, right? And when we increment, what do we get? The same thing. I mean, so basically what we want is, we want the same underlying state. We have the same pointer to this array, but we want to change the behavior just a little bit. We want increment still has the same semantics. We'll still go to the next element as before. Decrement will have the same semantics, but dereference will have slightly different semantics. Instead of giving you a reference to the entire thing, you'll get a reference to just the second part of it, right? So that's what I mean by an iterator adapter. We want to write a class that will behave like an iterator. It'll be implemented in terms of some other underlying iterator, but it'll have slightly different behavior, right? Is it clear what we want to do?
I mean, you could do something which iterate where which points to the end, it just points directly to the second object, right? In which case the logic, the dereference is simple, and the increment is the one that has the special sauce, and then this is flipped up.
Yes, you could do it that way. And in fact, the increment would actually, I mean, when you increment, what happens here? You know the size of the object, and you have to add, right? If you were pointing here, you would add the same number. It wouldn't change. That's a little harder to express in terms of, I mean, this is easier to keep straight because we have, we don't have a natural pointer into these things which can be incremented by the size of the outer object. So it's just clearer to keep a pointer to the outer object and then sort of take the right part of it that we want. All right, so let us try to write this. And okay, so another thing here is the total number of operations you can actually perform on an iterator are quite large, right? You can increment, decrement, dereference. You can add some arbitrary number to it. You can do plus equals if it's a random access iterator. You can do minus equals. You can subtract 2 iterators from each. I mean, there are a large number of operations, but fundamentally, what can you do? You can dereference and you can increment, and maybe you can increment by a fixed amount in case of a random access iterator, or you can decrement. So there are really 4 operations, but if you looked at the actual number of operators you would have to implement for a complete iterator class, that's a long list, like at least like a dozen or so, right? So, so we want to write some small thing that just, what we want is, I just implement the basic operations and I automatically get the rest derived from it, right? So what we want to do is something like, ideally we would write some basis class that implements the basic operations, and then the iterator should be derived from that. So that's what we're shooting for. So let's write the, let's call it second iterator basis, which will be iterating over the second of everything. So template, some kind of iterator. Let's start with forward. Okay, we'll figure out how this all fits, but let's, I mean, so we said this needs, what are the operations it needs? It needs a dereference, and it needs an increment. And it needs some state, the underlying thing we keep, right? So it will have some position. And how will dereference be implemented? What will dereference return? The value type of the iterator, which will be the type of the second, right? So okay, we need some affiliated types as well. So let's put in the affiliated types that we need. Value type of the iterator is going to be basically, we have I, right? It's the value type of I second. That's what we need, right? And you would typically write this by doing something like extracting the value type from the underlying iterator and then taking the second type. The pair has an affiliated type called second type and first type. So you could do that. In C++11, there's a simpler way you can do this. So let me just show you that instead, because it is easier. You can do type def decal type of So decal type just says, here's an expression, find its type, that's the one I want. That's what we'll get here. What other affiliated types do we need?
How does it even know that there is a second at all in there?
If there isn't, it will fail to compile.
Okay, that's how
I mean, basically,
instantiate one of these of something that doesn't have a pair.
no, but it's a good question in that we haven't really been very clear on what are the requirements on I, right? We've said I is an iterator, but really it's a little beyond that, right? We have to say, okay, if X is of type I, then X arrow second is well formed. I mean, you can say something like that. And if and when concepts get added, someone will have to figure out how to express this. That is not my problem, so let's move on. All right, so we have this type, what other affiliated types do iterators have? Reference type. So let's define that. Type def. What will be the reference type in this case? Value type reference. Reference. What else? You can just anything else? Well, we'll get to it if we need any. Okay, so dereference returns a reference. And what does it do? Return star, do we need a star? Position, arrow, second. That is it. That is our dereference, right? And we need an increment. What will increment do? Position plus plus. Plus plus position. Much better. As we know, post increment is evil. Yes. Okay, so we've got our increment, we've got our dereference. That should be enough. Increment needs to return something. What does it need to return? Void would be a good thing, yes. Any objections?
Yeah, it needs to return itself.
Why?
That's how iterators work.
Yeah, but this is not an iterator. This is a basis class that we will use to define our iterator. Right? So, well, the current position? If you want the incremented position, I mean, you can dereference. Why would you return it? What's the point?
Everything the iterator would decompose.
So you can call increment dot increment dot increment. That could also be a good argument for not returning, but regardless. I mean, why is post increment anyway? Let's implement the iterator, right? So it's templated on some kind of basis class. So it's B iterator. Okay, so what do we need? We need an object of type B, definitely.
The name of the struct iterator or something else?
It's iterator. Why not? We can, let's write it, and then if you feel the name should be changed, we can change it, right? Okay, we forgot something in the basis. We need to initialize it. So it has to be default constructible and initializable via, how are we initializing it, right, over here? We basically want to be able to initialize these things via the underlying type, which will work just naturally, actually. So we can leave it. All right. So we have a basis. The iterator needs a default constructor, which can just be like this. The iterator needs to be constructible from the basis, because that's what, no, not the basis, sorry. Okay, so this is an interesting point. Think about what we wrote here, right? Actually, let's clarify this a little, because this is not going to work at all. We will need to at least do something like type def pair int p. Okay, when we create these things, we have to give it some type that you know. So it's probably going to be p star. Actually, that right? What? Because this is all defined in terms of, we have an iterator, and we want an iterator over dot second of that. So you could go both ways on this, I think. So again, let's this is something. I mean, let's sort of put this in temporarily and see if we want to change it. As we write the code, we can come back and change it. All right. So what were we doing? Okay, we were thinking about how these objects. Okay, so this iter second is going to be an object of this type, the iterator type, right? And over there, we are constructing it from this other thing. We were calling begin on our array, and we were trying to construct it. So what type are we constructing it from? We're using the underlying iterator, right? And so basically what that means is we need to say here what the state type is. So we need another affiliated type here called, oops, state type. And now we can actually write this constructor, because now we know b : state type x. What?
You can't just use state type like that. You have to say type def b : state.
I have to say type.
Sorry.
Actually, or I could, I probably need a whole lot of affiliated types here as well. So I might just say, or yeah, type def, type name b : state. All right, this should simplify things. We have our state type, and we said that the basis has to be initializable from the state type, so we'll just do basis of x, and that should be sufficient. All right. Where? Well, yeah, true. Okay, so now let's implement the operators we need. Oh, yes. Anything else? Good. Go ahead.
Why does dereference return the type of reference to the value type?
Okay.
The type of business second value type rather returning?
Because we want to be able to say star foo equal to 7, for example. So this has to be something we can assign to. And if this was a value, you couldn't assign to it. All right, so let's implement the operators. The first one, dereference. Let's implement dereference. What does it return? It returns reference, operator star, and how will this work? Any guesses? Basis.deref. Yes, exactly. Return would help. Okay, so let's define type def, type name b : reference. Anything else? What else do we need? We should probably do all of them.
All right, now so far this is just glue. It's not doing anything.
This is just glue. The whole point of the iterator class is to be glue so that any interesting iterator you want to write, you just write these two functions. And then you can instantiate it, and it all works.
But so far we haven't seen any reason why we have that other class.
Once we implement all dozen operators that the iterator needs, it will become very clear why it exists. So, I mean, we've just gotten started. Let's write, because, I mean, shall I list them? Star, arrow, square bracket, plus, minus, plus equals, minus equals. And then there are like 3 or 4 different pluses you need because it's iterator plus difference type plus iterator.
So we could have written it all in one, but you want to make a very strict separation.
We can write it all in one, but then what that means is every time we write an iterator, we have to implement 1 dozen operator functions, all of which have the same content. I mean, they do nothing. It's the same way. You know, why do we think that something like inequality should be synthesized from equality? Because it is always that. The semantics of the language say that that is what it must be. There is no reason for it to be something else. Here it's a little, you know, this is a concept, but that you could argue, well, you could argue this is baked sufficiently deeply into the language that they should be in the standard library, and there's a proposal to do that, by the way. But regardless, often you have a concept where, or some type like array, we implemented the array, right? And that had a whole bunch of methods, and you want a rich interface there because you want it to be usable. You don't want to force someone into everything is just begin and size, and you can implement everything using that. I mean, yes, you can implement everything using that, but it's terribly inconvenient, right? So most of the methods there could probably be transplanted into any container and they would just work. It's the same case here. You need all of these operators. They can all be implemented in terms of increment and dereference. So you want to have standard implementations done once, and then whenever you want to write an iterator, you implement your dereference and it all works. That's what you want, right? So that's why we are doing this. And we are going to write multiple iterators, hopefully, which will all use this. Was that sufficiently convincing, or do you still have doubts? I think once we finish this, you will see very vividly why you need it. So let's continue. What's the next operator we should define? Arrow? How about arrow? Tell me how to define arrow. It returns a pointer. Operator arrow. Yeah, and we just take the address of that. But another thing here, what we should do is, since we know how to dereference already, we should implement arrow in terms of star, because it's right. So we do something like this. Operator star. And I forgot the return. Clearly, I've been doing too much functional programming lately. All right, we have the basics. What else?
But is reference defined? Like, you define what is operator star and operator arrow.
Mm-hmm.
How you use the reference.
Yes.
So that is defined by the language?
Yeah, that's defined by the language.
And why the star is not defined by the language?
Because think about what we are trying to do, right? Star is defined by language for the pointer, but we are trying to change what happens when we do star. If you have a pointer to this thing, you do star, you get the full object. What we're trying to say is, I want this object which still points to my pair, but when I dereference it, give me just a second. So we need to override that. We need to give it a different behavior. I mean, that's the goal. That's what we want to do. We want to be able to call any algorithm using these iterator adapters. let's go on and hopefully it'll be clear. If not, you can ask me again. Right? There's one very important thing we are missing. What other operators do we need? Increment, yes. Tell me how to implement. Come on, you guys are supposed to be writing the code here, right? I'm just typing. No, you can't do that here. What does when you call plus plus, what does it return? I mean, here we are implementing an actual iterator, so it has to do what? Basis or increment is what we will do, but what is the signature of? Yes, exactly. So we need iterator ref operator plus sorry. And let's implement pre-increment first. So why am I not using tab? Because I can't hit it. Yes. We call basis dot increment, and then we have to return ourselves. How do we do that? Star this. That's it. This is our increment, and we need a post increment which returns a copy. Okay. Iterator TM. This is something that arguably should be synthesized by the language because there is no other way to do it. Well, there are, but never mind that. Only in very special cases. So temp equal to star this, increment, return temp. Right? So if you were writing an iterator from scratch, you would have to implement this. Already we are, we have 4. What else does a forward iterator have that we need? Can you compare forward? Yes, equality. You can do equality. You can't do less than, but you can do equality. So how would we implement that? Friend operator. Yes, that is a good point. And it takes two const references. Iterator ref, if I spell it correctly, iterator ref x, const iterator ref y. And how do we compare them? We have to compare the underlying state, exactly, right? So which means we need a method to get the underlying state, which we don't have yet, right? But we will write that. Return x dot state basis x dot basis dot state equal to y dot basis dot state. Yes?
Why don't we define equality on basis?
We could do that. We could say that basis must be a regular type and must have equality defined, right? But take a look at the example we have here, right? Where did it go? In the vast majority of cases, our underlying type is going to be a pointer, right? So we will have some underlying pointer, but we'll want to change its increment and dereference semantics a little bit. And then we would have to write an equality function that compares those pointers, which we could do, but it's just extra work. Instead, if we say that the state type is regular, and that must have equality defined on it, then that makes the job of the basis class writer becomes much easier, because now the basis class just has to be semi-regular, and since the state type, which is a pointer in the vast majority of cases, is already a regular type which has equality defined on it, you don't have to do anything special. And only if you have state that is a little more complicated, then you'll have to make sure that equality is defined on it. Right? So it just makes it easier.
But the basis is almost certainly going to be an iterator.
Yes.
So it's going to have quality defined on it to useful iterator.
Yes, which is why we don't want to have to re-implement equality in basis.
Oh, I see.
Right? So we haven't actually written. Right, I think now we know enough. We should probably say what we mean by basis, right? Iterator basis is something that is semi-regular, which means it can be default constructed, copy constructed, few destructed, a few other things, but it does not need to have equality. Right? But it needs to have a bunch of affiliated types, which we've used. Value type, reference, pointer. We probably need an iterator category, which we will add. It needs a deref function, which returns reference, and it needs a increment. Increment, which returns void, and it needs a state, which we will add now, which returns state type. Yes, absolutely. All right, reference, pointer, value type, state type, iterator. Let's add iterator category. That's going to be std. Since we are only doing forward iterator for now, let's make it a forward iterator. Forward iterator tag, I think, is what it is. All right. What about state type?
It's already forwarded.
Anyway, state type, state return position. Now we can implement, well, we have implemented this already, so now this will work. We also need and that is very easy to do. We spent the last 2 lectures talking about it. So I will not belabor the point. Yes? Okay. And let's add iterator category while we are at it. Type def, type name, iterator category. All right. I think that's all that we need for a forward iterator. So we have one missing piece here, which is we're doing this thing with, we're saying iter second of p star. We haven't really defined what iter second is, right? So how would we actually create this? What you'd have to do is yes, exactly. So the type is going to be something like iterator of second iterator basis of p star. Right? That's what the entire type is going to look like. And to make this a little prettier, we can define a type function over here. template, input iterator, forward iterator. Using second iterator equal to iterator second iterator basis of I. Right? Now we can actually write, oh, let me keep the names consistent. Okay, now we should be able to write this, and it should print. Yes? Let's see if it works. What are the chances it will compile? Well, right now none, but let's fix the obvious things. Include iterator. What else do I need? I might not need anything else for now. That's right. All right. Oh, yes. Define iterator basis. We should put all of our concepts in a .h file. Did I define that? I don't know. I think those two might be the only ones. Member function state not viable, but function is not, yeah, that needs to be const. Deref, no, deref should not be const. Why should deref be const?
Because if the iterator was const, you could still dereference.
If the iterator was const, you can still dereference it, but then you return a reference type. Is that going to be a const reference? That's the thing we have to make sure of.
The problem is the terminology. When we say const iterator, what we mean is an iterator to a const object, because we almost never work with const iterators. But if you did have a const iterator, it would be legal to dereference it, and what you dereferenced would in fact not be const. Just like if you have a const pointer, you can't change the pointer, but you can dereference it and modify what is the pointer.
Yes, yes. So if, yes, so basically, did everyone catch that? If I is pointing, if I is a const iterator, everything is fine. If you have a const iterator object, but we almost never have a const iterator object, except when you, well.
Yeah, I think it should be correct, even though you're right. We almost never have a true iterator that is itself const. That's
Yes.
almost never the case.
One thing I'm not sure of is, yeah, I think that's fine. Okay.
And then in your iterator definition above,
Yes,
the dereferences up there could also be.
they have the same. Let's see. It works. So just to recap. Let's fix the things that John pointed out. So John, tell me what all should be const.
That function there, if you were on the reference function, should be const.
Yes,
And the
and the deref should be const, yes. These are all modifying, so these should not be const. And these are friends, so, okay. So already I think we can start seeing some point to this helper class, because we have a whole bunch of methods, but if you want to define a new iterator, we simply define this little basis class, which has a dereference, an increment, and then we can, you can write wonderful things like this, and it actually works. And you could, so for instance, if you wanted to sort on the second element, you could call standard sort on this, and it would work without having to write any other code, without any extra overhead, in fact. Let's break for lunch, and we will resume afterwards.